Alright, so we're in Windows World again, and this is quite a cool office, man. Nice drum set. So that's how you get your stress out,
That was the
late
thought.
at night coding?
Although you can tell from the dust on it, I've been working a little too hard to play lately. So.
Okay, so who are you? What's going on?
I'm Jon Cargille. I'm a developer in the Windows storage team, and I own the Kernel Transaction Manager.
Alright.
Which you've probably heard of in relation to the Transactional File System and the Transactional Registry.
Excellent. Who are you, sir?
I'm Christian Allred. I'm one of the developers for Transactional and TxF, and we work together with the Kernel Transaction Manager to provide user-level transactions in the file system.
Fantastic. So we should probably dig in today a little bit about the architecture. I remember I talked to Surendra, I guess it was like a year ago now.
Yeah, it's been a while.
And I remember popped in your office and it was like, cool drum set. You know? And Surendra was saying you definitely need to talk to Jon about KTM.
Yeah, we were talking about having that conversation.
Yeah, so let's start digging into that a little bit, and then we'll move into people that utilize your services.
Sure. So the Kernel Transaction Manager sort of exposes the kernel and user APIs for interacting with transactions and related objects. So if you're writing client code, meaning you just want to use transactions, you're not providing them to other components, then the APIs are really simple. It's just create transaction and then commit or rollback transaction. So you basically just use a transaction to wrap a bunch of other operations, in the file system or in the registry, and then either atomically make all of them happen or none of them happen.
Understood.
And we guarantee that across, different disks, different systems. If you use the distributed transaction coordinator above us, and so
cool.
In a nutshell, the KTM provides these abstractions. It actually provides other abstractions if you're interested in working with transactions in the same way that the transactional file system does. So if you want to expose a data store and take part in transactions and make your data store be consistent with other data stores, then we have another set of objects and APIs that you use to do that.
Fantastic.
But for most users, it's really simple. Create, commit, abort, or rollback.
But I mean, the developers need to think carefully about what they're doing inside of the context of the transaction. Right?
Yeah, they do.
Like a long running. So I mean, there's something that we need to think about. What are some of the situations where people should just use to use the transactional file system KTM just off the bat? Like I'm designing this application for Vista. This is a Vista component. It exists in Vista, and I believe in one of the server SKUs.
Yeah, the upcoming
Longhorn server. So this is a new Vista kernel component that people can take advantage of to doing file I/O. Correct?
Yeah.
Yep.
So let's talk a little bit about when would be the appropriate times for people to use this. I mean, use it all the time. I want to guarantee that it's either going to succeed, everything succeeds, or roll back. I mean, why wouldn't that not be a good model always?
Well, it would be a good model in cases where, say, you wanted to make changes to a bunch of disparate files, and you wanted to make sure that they were all consistent. These days, people usually have to do their own error handling in these kind of cases, and they have to keep track of the changes they made, and they have to keep track of how to fix them if something goes wrong, you run out of memory, you hit a disk error or whatever. But with TxF, when something goes wrong, the transaction just rolls back. The system undoes all the stuff that you did. So error handling is one of the big wins, I guess, for using TxF.
Sure.
Is you don't have to worry about undoing the work that you did yourself. It just happens.
Excellent.
And you can also trigger that kind of a rollback if the error is in your own application. If your application encounters a situation, some kind of problem, then the app can just say rollback transaction, and it's all done.
Excellent. Now, there's a lot of magic that's going on there.
There is magic, and I would also point out there are times when you don't want to use transactions. The simplest example I can think of is, say your app keeps a log of everything it does, and it just, for later auditing or that type of thing, and say your app puts errors in that log. Well, the last thing you want to do when things go wrong is roll back and undo your log of why things went wrong, so you can't diagnose it later. Right? So there are definitely some file updates that you don't want to do transactionally.
So you do that on a different thread, or
or well, you can even do it on the same thread, just a different handle that's not transacted.
Yeah, because the programming model is such that your file handle is the thing that is bound to the transaction. So you start a transaction, and then you'll call a new Win32 API, create file transacted. And the file handle that you get back out of that is bound to the transaction that you specified to create file transacted. And so any subsequent reads or writes or any I/O operations on that handle are transacted automatically. And if you just use regular old create file, the handle you get back is non-transacted. So then you could have a transacted handle and a non-transacted handle in the same thread.
Sure. Excellent. Cool. So let's dig into this. Let's come on, man. How'd you guys implement this? I mean, most people understand transactions, right? The atomic nature of either.
Yeah, they have the ACID properties, right?
You got
Atomic,
it.
consistent, isolated, and durable.
Now, for you guys actually to pull that off, to make it easier for developers up in whatever land they live in, you have to do a lot of work under the covers. So what's the architecture of KTM?
We do. So, let's see. KTM. Start with the picture. So basically, KTM is a kernel component. So it's it's down below the user kernel boundary. It exposes there's a set of Win32 libraries that call down into KTM through the basically the kernel system call layer. And you can, so we expose a set of kernel APIs, at this level, NT and ZW APIs that people can use to call our services from the kernel. We expose Win32 to user mode, and clients like TxF and TxR call into us through these APIs. We below us we make use of we have a log file for logging transaction prepare commit records, and that's implemented by CLFS, the Common Log File System. It's basically a general log provider, and that's kind of the architecture in a nutshell. We have state machines in here which keep track of basically the state of all of these different transactions and the set of operations that are legal to do with them. We also support having superior transaction managers, so you can basically have a transaction manager stack, sort of. There's already an existing transaction manager on the Microsoft platform called the Distributed Transaction Coordinator. You can use it to coordinate multiple SQL servers and that type of thing. So basically there's integration here to have these guys work together on a transaction, in which case they'd be what we call a superior TM.
Okay.
The KTM itself is implemented in terms of a set of OB objects. So the OB is the generic object manager in the kernel.
Okay.
Your event objects, your semaphores, your I/O completion ports, your file objects, all of those are already existing types of OB objects. So we actually created 4 new types of OB objects. There's a transaction. Transactions get logged in TMs, which are represented by a log file, and then there are RMs, which are resources that take part in transactions. So every TxF volume is an RM, every registry hive is an RM. And then RMs enlist on transactions, so the state of the relationship between an RM and a transaction is represented by an enlistment object. So those new object types get exposed, and APIs to manipulate those object types.
Excellent.
State machines to keep track of the state of all of those things.
So I mean, that's cool.
That's
I mean,
it in a nutshell.
a lot of times, people would wonder what it is that you're doing to really enable this ACID construct, right? I mean,
Okay.
it's one thing to say like, okay, create this object and do your operations, and we're going to make sure that it's a transactional operation. If anything goes wrong, we'll let you know, and you can roll back.
Yeah.
But what's going on underneath the covers? You're saying is creative use of state machines and these new objects.
So I guess I could give you a little more detail there. So the transactions, we use a a process called two-phase commit, which probably most people have heard of, to make sure all of the resources are in a state where before we commit, we make sure they have all of the information they need logged in order to go to either a committed state or an aborted or rollback state. So it's write-ahead logging is what the resource managers do. So take a little example. TxF has a log file here, which you can think of as just a stream of bytes, right? So you end up with a file getting created transactionally. Well, TxF will generate a log record for the create, and for all of these different, say you create a bunch of files, every one of them will generate log records, and then say you committed the transaction, and we'll gloss over the fact there's an optimization if there's really only one RM involved, but if there's more than one RM, then KTM will send a prepare to the TxF, and TxF will log the fact that it's prepared. And then that basically says, okay, I know everything I need to do in the transaction, I've got it all durably stored on disk, and now I know that I can apply all that. Say the power goes out right after the prepare record hits disk. In recovery, we'll come up and we'll have this dialogue about what really happened on the transaction, and I'll tell TxF that it committed, and then it'll make sure that all of those things are durably applied.
Excellent.
So the 2PC is sending out the prepares to everybody that's involved, and then KTM actually logs the outcome here in its log. It says, oh, by the way, this transaction committed. And that way, once the commit record hits disk, the transaction is committed for all time. This write is the one that determines whether it commits or rolls back.
TxF maintains enough state in his log so that he can reconstruct what happened in the transaction based on what's in the log. Because, as you know, the file system's got a cache, so a lot of times a lot of the bytes that you actually write to the disk are sitting in memory for an indeterminate amount of time. They may not get to the platters immediately. And so what TxF does, though, is when he's told commit, he ensures that at the least his log records make it to the disk.
When you still prepare, right?
Right, in prepare, in this scenario, in prepare, TxF makes sure that the log records are durably written to the disk. And so even if the power goes and the cache is lost, it doesn't matter because everything we need to redo the transaction is written in these records.
Got it. And you do that. That's the first thing you do, right?
When we're told to prepare, we take a number of steps, and the key is that before we turn around and tell KTM we are prepared, we've written this record, so that when we tell them we're prepared, we truthfully can make the operation durable if we're then told to commit.
Yeah, and force the log to disk up to that point.
Excellent.
Everything before that in the log has to go.
Because we can always fail the prepare, which would cause the transaction to roll back. But once we tell KTM that we're prepared,
You're committed.
Are committed, essentially. Yeah.
You're committed to the commit.
We're committed to the commit.
You're committed to do whatever KTM tells you.
All right. Very cool. Well, I mean, it looks like these are new constructs down in kernel world. So this is new, right?
Yeah.
CLFS.
CLFS was new in R2 actually.
Yeah.
Okay.
They went out before the rest. TxF and KTM and TxR all went out in Vista client.
Cool. So let's like the transactional registry. That's an interesting concept. So you would use that to ensure that, say, during installation.
Yeah. If you're an installer, a lot of the things that installers do involve both file system and registry operations, and they certainly want to ensure that all of them take place together. Because you don't want to be left in a state where you've got phantom registry keys floating around referring to files that don't exist, or worse, applications that don't have their registry entries but have their files on the disk. So you can do things like start a transaction, write your files, write your registry changes, and then commit it, and you can be assured that they're all there.
That's awesome. So that's important. So for people writing installers, think about using TxR.
Huge simplifier.
Yeah. Vista Client System Update uses transactions. Every time that Vista downloads updates for the OS, it applies them in a transaction.
Excellent. You mean we use our own innovations?
We do.
People always ask, how come
we're
you guys...
dog-fooding it.
Right on, man. I mean, it makes perfect sense. And so, because you've exposed this up in Win32 world, which I'm assuming COM, or not?
You've got there, Win32, but there's also, I've been made aware, there are also managed code APIs to use transactions.
Yeah, there is. There's a whole new set of managed APIs called system.transactions.
Yeah, that's right.
Excellent.
And so that's sort of the managed world. This is, Win32 is not the same as COM. It's a lower level API. Create file, create event, that style of programming.
Calls into the kernel.
Yeah,
stuff.
it calls into
Yeah.
the
The Win32 APIs they call
kernel system.
the basic system APIs, the NT level APIs that actually make the transition into the kernel.
Yeah.
Yeah.
You can make use of KTM from, since you mentioned COM, you can write apps that are targeted at DTC using their DTC proxy, which is called OLATX. And they've exposed a new method. I'm not going to get the exact name right, but basically it's a get KTM handle method on an iTransaction, I believe. So something like that. And you can basically create a DTC transaction, do some work, say on a SQL server, under that transaction, then get the KTM handle and use that to do some file system work. So you can coordinate and have consistent updates across SQL and TxF or TxR.
Yeah.
Very cool. Nice.
It is pretty cool stuff.
Yeah.
The other part you mentioned, you were asking about how we actually pull all this together. The other parts of the ACID construct, the isolation part in particular, that's the job of the resource managers. And TxF is one of those resource managers. And so he does a lot of work to ensure that while a transaction is ongoing, the changes in that transaction are visible only to the transaction and not to anybody else. So if you create, say for example, you create some file or a bunch of files in a directory, and some other user on the same machine comes along and types dir at the command prompt, he won't see those files until the transaction commits.
Okay.
He won't see anything you've done until the transaction commits.
Excellent. And that's a good point. So the consumer of KTM is responsible for part of the equation for transaction, right? As you just said, for isolation, you own that.
The resource managers, yes.
The resource managers.
are
So that's
responsible for
different than
isolation.
those that. So you have TxF, TxR. Conceivably, there could be more constructs created that
Sure,
leverage
could.
KTM.
Other people could write other RMs in the kernel. Say if they have some other store, people can write other RMs up in user mode. Say you wanted to take the JET database and make it play in transactions with SQL or TxF. You could write to our Win32 APIs, which support doing resource managers in user mode as well.
Very cool.
So we're hoping that as time goes on, hopefully more and more things that act like data stores will support transactions, and
Certainly.
then the power of the transactions across those stores grows. There's sort of a network effect there.
Absolutely. And then someday memory management will involve transactions.
Yeah.
There is actually a team you might want to talk to.
Yeah, there is actually a transacted memory team that is kind of working on that kind of thing.
Yeah.
Yeah.
Well, I interviewed Simon Peyton Jones when I was over in Cambridge, and we talked about they're adding transactional memory to programming languages.
Yeah.
So, like in C#, you would say atomic,
Yep.
write your code, close curly brace, and that's a transactional construct that you use just like you would for using,
Transaction
which is
memory
pretty cool.
updates. It is.
You
It's
got
a pretty
it.
cool programming model.
and solves a lot of the problems with shared memory, which is a disaster
Yep.
in the world of concurrency.
Yeah.
Very cool.
So,
So what else is going on here? You guys are the developers behind this. You normally aren't on camera. Get you guys.
We
here.
usually try to stay under the radar.
So
yeah.
how long?
Yeah.
You were mentioning that it took 5 years. You've been working on
I've been
TxF
working on
for
it
5 years.
but
Yeah.
I started at Microsoft about 5 years ago, and I've been working on TxF the whole time. But TxF and KTM and all was in the works for a couple of years before then.
Yeah.
Mhm.
I joined the team just after Windows 2000 shipped.
Cool. And so let's talk a little bit about the history then. I mean, why did you create this new problem? So in other words,
No, it's a new solution. Not a
you
new
know,
problem.
that's what I meant, of course. But when you have a new feature, it's a problem you have to solve as a developer. So I always
Yeah.
think about it in terms of creating new problems to solve.
Yeah, the motivator for it, well, I guess transactions are a pretty mature technology. They've been around for decades. And it, I don't know, it seems like a lot of the code that developers write is cleanup code. You know, you do some work and then you realize something hasn't gone the way you want it to, and you have to undo some of that work.
Mm-hmm.
You know, you can end up with your finally cleanup clauses being bigger than the work you were trying to do to begin with. So one of the things we were trying to do was say, let's take this transactional technology, push it down to a deep level of the operating system, and try to make it easier to write applications.
Sure.
So
Which of
that's
course
kind
will bubble up to the user.
Yeah.
Right.
We're hoping users can definitely write, totally new client apps up here that are transactionally aware,
Mm-hmm.
that are simpler because of being able to use, all of this technology.
Sure. So like if I wanted to back up, or not can you say back up, but why not back up? But if I'm a user and I want to do some operation and not lose data,
Mm-hmm.
Yeah.
and something catastrophic happens,
Yeah.
transactions are a wonderful way around that. We don't have that in earlier client operating systems that we've released.
Particularly in the case of a catastrophic system event, like the power fails or
Yeah.
whatever, or a disk head crashes, or well, maybe not a disk head crash, but the power failure, for example, right?
Yeah.
If you're doing some kind of multi-file update, you're updating your website, your corporate website or something horrendous like that, and the power fails halfway through, you have no idea what state your files are in. Half of them are there, half of them may not be there, half of each individual file might be there for all you know.
Yeah.
And so one of the great things about this is when the power comes back up, we go through what's called recovery, where we read our log, and any transaction that was half done, that was in flight at the time that the system went down, gets undone at the time that the system boots. So everything that was in a transaction is then consistent. You know that you're not going to be left in some half weird state that you're going to have to maybe scan the whole disk to figure out how broken you are to fix. It's just going to get fixed.
Mm-hmm.
Excellent.
Yeah, I would actually point out this stuff is valuable even if you're updating a single file. If you suppose you open a file for overwrite and you're writing out your new contents, and halfway through your write the power goes off. What do you have left on disk? It could be a real mess. The beginning of the file might be the new version, the end of the file might be the old version. So apps have historically been written to work around that problem by writing it to a new name.
Like Word.
Like Word. This is exactly what Office does. They write to a new file, they move the other one aside, and then rename it into place. So even with a single file update, with transactional technologies, you don't have to worry about all that stuff. You just open it and write it, and you either get, if the power goes out, you get either the initial state or the fully written state. You never get the in the middle messy states.
Excellent. And I guess I'd also ask, since we mentioned memory, but we really can't talk about the future of Windows and stuff because I'll get in trouble. But with KTM, I could conceivably just use that to deal with any type of construct, any type of thing that I want to be done in an ACID way, right? Right now, we're always talking about file I/O, and that's taken care of here, right?
Yeah.
But there could be some other, conceivably, one could think of other ways, other things you'd like to have happen in a transactional context. That isn't file I/O.
Although I would say anything that it does depend on how heavyweight the operation is. If you're talking about transacted memory, then using a KTM Resource Manager API would probably not be the right level of abstraction, just because there is overhead of doing these kernel traps. So really, we sort of already have a transaction manager architecture that's layered in a way. The KTM is sort of the deep in the heart of the kernel one. We've had this user mode one for a long time, and the system.transactions/DTC team has been working on something that they call the what's the name of it? Lightweight Transaction Manager, something like that, or LTM, which is sort of an in-proc TM for. So if you were doing transacted memory, you'd want to use something that's lighter weight and doesn't have to trap into the kernel, I guess is the message. And we sort of have, the architecture we're moving towards as a company is sort of a layered, you start with a very lightweight TM, say they're in memory TM, then as you touch more resources, you sort of go to a heavier and heavier weight TM.
That brings
Not
up a
that
good
KTM
point.
is necessarily the heaviest weight one. I wouldn't want to say that.
No, well, it's down in kernel land.
It is down in
man.
kernel
You can't
land.
be that heavyweight.
But sometimes getting to kernel and back out is actually cheaper than going process to process. So
Wow.
it depends on what what the communication mechanism is.
Well, is it fast RPC? I mean,
No, these are just kernel traps.
Okay.
Into the kernel. So the same ones you get millions of every second
Very
when you're
cool.
running.
So let's talk about that. I mean, it was kind of my convoluted way of getting to the question of what are the performance implications of using transactions. So if I write an application, I'm like, wow, this is so cool. I want to make sure everything is in a transaction. And, maybe I don't quite understand what that might mean from a performance perspective, and Rico Mariani might, like, what the hell are you doing? So.
Do you want to answer that one, Christian?
Well, there is an overhead to using transactions, of course, because you're doing, for one thing, at the very least, you're doing more I/O, because you're writing to the log as well as writing the things you were going to write in the first place to your files. Overall, the hit is actually pretty negligible. It's only in the realm of 2 to 5%, I think. That's what we've clocked it at. The benchmarks that we've been able to do so far, and it might also be good to point out that it's a pay-for-play model, right? Regular old NTFS, if you're not using transactions, you won't notice they're there. There's no overhead introduced in the regular paths. It's only when you use transactions where you essentially, you're paying for all these extra guarantees.
Sure.
But, like I said, the overhead is not so bad.
That's not bad at all.
No, it isn't. For TxF, internally, part of the reason we can do that is because TxF is written to optimize for the commit case, right? We assume that people want their stuff to happen. They would prefer that it not happen, So in TxF, what really happens is as you're doing your IOs, your file IOs, everything is actually going to the disk the way that it always did. And in memory, we set up these isolation structures to make sure that people who are not in your transaction can't see your changes until you've committed. So that makes it so that commit is a relatively lightweight operation. We just write a log record, flush it out to the disk, and we're essentially done. It's essentially just one I/O, because all the I/O that you've done so far in your transaction is already on the disk. If you abort, if you roll back, then it becomes heavier because we actually have to go back through the log and undo all this changes that you did on the disk, right? But like I said, that's the less common case. Most of the time, people will commit their transactions.
Sure, they won't roll back.
Right.
Interesting. So, I mean, that brings up a good point. I mean, what exactly are you doing in a rollback situation? So, you've already logged what the person has done. So, let's say I have this massive, I have set up a transaction, and what it is go through all these files and make some changes to every file. So, I open up all these files, and I start to make changes. Like, I want to add this little thing in all the files to represent something.
Okay.
And then I say roll back, because maybe I'm listening on to a different thread about some other information that I need, and all of a sudden that thread, something bad happens, like I need to get the information from the internet to stick into the file.
Sure.
Whatever. So I say roll back.
Okay.
Tell me what happens.
Well, as you're doing your changes in the forward direction, right? As we call it the forward direction as you're doing your changes. We're writing these log records that describe the changes you're making. But also, we know that the possibility exists that you may need to undo all these things. So the scenario you had was you take a bunch of files and you may write new information somewhere in the middle of your files, right? So what TxF does is he keeps a special hidden system file called $tops, the TxF old page stream, right? And it's this great big long circular buffer, essentially. And every time in a transaction you go and you overwrite a part of a file, first we take the old part, the part you're going to overwrite, and we stash it away in here. And then we let you write on that page.
Okay.
And so what happens in rollback is the first thing we do is we start reading backwards through the log. We get the last log record you wrote, and we look at it, and it describes the operations you did, and it also describes how to undo them. And we go and we undo it. And then we follow this chain of log records backwards through time, through the log. And for each log record, we undo what the log record says that we did. So in this case, we would go back into this tops file, get the page in the tops file that we overwrote, and stick it back in the original file. And the log record contains all the information we need to quickly and efficiently find this page.
Okay.
and find where it went in the original file. So we stick all these pages back into the original files. We undo any deletes you did. We undo any creates you did. We undo everything you did in the transaction.
Okay.
And then we're done. You're back to the way you were before you began making changes in the transaction.
And to actually pull that off in the normal sense that we, as Windows developers are used to using, that would require a heck of a lot of code on my part, or on the developer's part, to do exactly the tops thing that you're talking about. I'd have to write that myself.
You'd have to be remembering everything you did.
Replicate all of this behavior,
Yep.
except as the app developer, you'd have to do it for every operation that you did, and you'd have to be doing it by continually calling back and forth into the kernel, right?
Exactly.
Here we do it all
And
for
there
you.
are also times
should
when
be
it's
that case.
really hard to remember what to undo. You know,
Right.
it's easy if you're just dealing with an internal failure, but if the power went out and you come back up, you'd really have to
Exactly.
replicate the functionality of having a log that, you know, durably remembered all the operations you did.
That's
Yeah.
awesome.
For most apps, when the power goes out, that's it. The app is completely over.
Totally. And we've all had that happen.
Yeah.
Okay.
But here, everything's durably written in the disk.
Great.
When the power comes back up, we'll scan through the log, we'll see that there's no commit record for the work that you did, and we'll do this rollback stuff for you.
That's awesome. I mean, and that's really the way it should be. I mean, when you think about it, file I/O, these low-level constructs on an operating system, this stuff should happen for me as a developer.
Sure.
The system should own ensuring that even if I do something wrong, although that's kind of vague, but if something happens outside of my
If you
control,
can't complete the set of operations that you wanted,
got
then
it.
do you really want half of that set of operations?
no, not at all. And one of the things that could be interesting is what's the scenario when I'm dealing with a file copy across the internet, or a file copy, say, over WebDAV to some web server somewhere, and then all of a sudden either the server shuts off. I know that's the DTC model, but I'm talking, say I write a client app and I'm trying to send files over to another machine that's running a server that I wrote, say, also using transactions, so I can communicate intelligently. Is that how that would work?
It seems like an important scenario. We actually did have plans that we were considering at one point to tunnel.
But wait, you had to ship.
We did have plans to do this. We would like to do it eventually to make it really easy to have that happen.
Okay.
At the moment, the only way to do that would be to write to the DTC OLE TX APIs
Okay.
and use them for the transport to take the transaction to a different node. On both machines, you could call the get KTM handle API and do TxF operations.
And of course, that would be
But-
COM interop. if
Yeah,
you're writing
exactly.
a system transaction.
You would have to write that to the COM layer.
But
Yeah.
eventually, what would be great would be if all this stuff just flowed across in
Yeah.
SMB.
Yeah, the thought was we might be able to just tunnel that across SMB and have it be really, really easy to write.
Cool. Well, maybe someday, But for now, I mean, that's a beautiful thing to see, and it's unique to Vista and the Longhorn server. At least all of these components that we're looking at here.
Yep.
Some of them exist in server R2, like CLFS, as you mentioned. And clearly, this type of model would be incredibly useful in a server environment,
Oh yeah.
where you're constantly dealing with I/O at an unbelievable level.
Yeah.
But then again, you also require high performance. So clearly you guys have done great performance tuning work, is what I was trying to get. Like the speed at which a transaction happens, certainly it's dependent upon what you're doing inside the transactional start and end.
It does. Depends on how big the
But it's going to be
boundary
pretty
is.
fast. This is as fast as
It's-
I/O, except
it's-
for your couple, except you have to write to the CLFS.
Pretty low overhead for
Yeah, it's
the
pretty low.
functionality that you're getting.
Yeah, you're getting a lot of functionality for the relatively
Price
small
that you
amount of
pay.
overhead. Yeah.
Right on.
Yeah, we totally agree though. This is really, we think it's compelling even in client, although clients don't want to know about what's going on under the covers. But we're able to provide a higher level of, consistency in terms of applying updates than we've ever had before. So we were really pretty psyched that the Windows Update team, the CSI guys,
Yeah.
adopted this as an enabling technology for them. But in server, in the server enterprise space, consistency of their data is really, really incredibly important. So we think this is an even stronger sell there.
Imagine having some database application where you keep lots and lots of files, and you also keep metadata information about it. You could keep your metadata in SQL, and you can keep your files in a TxF enabled volume, right? You keep your files in just regular old Longhorn server disks because they're TxF enabled volumes. And you don't
Nice.
have to worry about storing them as blobs in SQL Server, which is really inefficient.
Absolutely.
Or you don't have to worry about weird inconsistencies showing up if the machine crashes and you don't know how SQL was relative to the file system at the time, because they all get coordinated together.
Wow.
Yeah, we have customers who are very interested in using it for that type of thing. One of the scenarios they described to us was like a brokerage having to basically maintain information about all of the emails their brokers send. And so they would store them each in a file, but then they needed to be able to index them and search them and have all of these structured data across them. And keeping those two consistent was a nigh on impossible thing to do without technology like this.
Absolutely. And again, focusing back on the client, this is going to really enable a new class of reliability for certain types of applications. I mean, my favorite, people love looking at pictures and changing pictures or copying pictures and whatever. So you could write an application where you can guarantee that the stream of data that I have coming from my camera or whatever, if it doesn't work, something bad happens, then I didn't lose what I'm doing. I mean, obviously the camera's not the best example because, hey, they'll still be on the camera. But let's assume you have the type of camera that you're sucking data off and it automatically deletes them when you're done.
Yeah,
Sure.
it's gone.
I mean, terrible idea. But my point is, you've enabled a new class of applications where the user can feel confident that if anything goes wrong that's outside of their control, the kid comes by and pulls the thing out of the wall.
Cable gets yanked.
You got
power
it.
goes out.
That they're not hosed.
Lightning strikes.
And that only exists in Vista.
Yep.
For the client.
Exactly.
Right.
We are taking the reliability and consistency of data to a new level.
Awesome, you guys. Well, thank you for your time.
Certainly.
And
Thanks for coming by.
it was great to meet you and finally start seeing some of the devs that made all this stuff real.
Thanks for coming by.
And thank you. And I have to show that Jon is clearly into plants.
I'm
So-
exploring my green thumb.
excellent. So I can tell the air in here is actually pretty clean. Yeah, it's got that fresh oxygen. Very cool.
Yeah, plus I just like to touch color.
That's nice. Hey, take care, you guys. Great work.
Thanks.
Thank you very much.